Okay, here's the announcement I was supposed to have made last week, but I didn't see the email until after the classes were over. So here's what it was. The vice president sent an email saying that as of now, 5 o'clock, about an hour ago, 55 minutes ago, let me phrase it correctly. If you haven't completed payment, and I think everyone in this class has, except for the people who haven't shown, and that was one of the issues with the one who said she was coming. When I emailed her the stuff, I said, well, look, here, Vice President sent an email that said everybody has to be paid by 5 o'clock on Monday. So please get that taken care of, or me sending all this stuff won't make any difference. You're not going to be in the role anymore. And maybe that's why she's not showing today. I don't know. But anyway, we're recording. Well, I thought we were. Yeah, we are recording. Okay. So let's get this set up from the present slide. So basically, all three of you are paid, I'm sure, right? If you know of anyone who hasn't, they need to get in touch with the business office, financial aid, somebody, as in close to immediately, to see if you can figure out, explain to them what's going on, what your plans are. Otherwise, you're going to be removed from the role. Now, you may still be able to talk your way back in, but it's effort on your part, and it's effort on our part too. So please get that done if you know of anyone who still needs to do that. All right. Good deal. Any questions on anything we've covered so far? All right, today we're starting with topic 18, direct current circuits. It was the same as chapter 18 on the old edition. Okay? So let's look at what electric circuits are and see why we mess with them. Electric circuits control the flow of electricity and the energy associated with it. Now, they talk about energy as if it flows also. That's a little bit of a misnomer, but the concept is there. Circuits are used in many applications, certainly. Kirchhoff's rules will simplify the analysis of some simple to fairly complicated circuits. Some circuits will be in steady state. The currents are constant in magnitude and direction. In circuits containing resistors and capacitors, the current varies with time. Now, so far, we've talked about capacitors, but haven't really made super big reference to capacitors in circuits. Well, we did, about series and parallel. Okay? We've done the same for resistors. Now we're going to combine the two, and I don't know in this course if we'll actually get to inductors or not, but they also will produce varying currents if we get that far. We won't in this chapter, but in a subsequent chapter. Now, this is a weird little phrase here. Sources of EMF. Does anyone know what EMF is? What's that? No. This is EMF is the old name for it was electromotive force, and they abbreviated that to EMF. But because it really wasn't a force, it was energy per unit charge, they decided to quit calling it force, electromotive force, but everybody still referred to it as EMF. So now it's just EMF. It doesn't really stand for anything now. The source that maintains the current in a closed circuit is called a source of EMF. Okay? Just call it EMF. Don't try to pronounce it ILF or something like that. It's EMF. Any devices that increase the potential energy of charges circulating in a circuit are sources of EMF. If you're increasing the potential energy of the charges circulating in a circuit, you're a source of EMF. Examples include batteries in DC circuitry, generators in AC circuitry. In other words, when you plug into a wall, you're you're increasing your potential energy. That ultimately came from the generator. When you have a battery, that came from the battery. The SI units for EMF are volts. And that's why I said it's not a force. A volt is a joule per coulomb. Remember? Energy per charge. So the EMF is not a force. That's why we don't call it an electromotive force anymore. It's a volt. Joules per coulomb. It's the work done per unit charge. Work in joules per unit charge in coulomb. EMF is work done per unit charge. So it's not a force, it's work. Okay? Per unit charge. Now, a real battery always has some internal resistance. Most of the time we ignore it, okay? But there are some times we do need to do it. Therefore, the terminal voltage is not equal to the EMF. And guess what? Who cares what the EMF is? All you care about is the voltage across the battery, right? So therefore, you tend to ignore the EMF and just do the voltage across the battery. They're fairly close, but not the same, because every battery has a little bit of resistance in it. Now, this shows, basically, that looks to me like a car battery, doesn't it, to you? Okay. Now, not too long ago, I'd say no more than, in fact, it was late May, just a little over a month ago. Maybe a little bit more than that. My wife's battery died. It was actually the first day of class this term. It was that Monday, first day of class this term. Wednesday, first day of class. Because I was in class all day long, never in my office, and my wife was calling my office all day long, and I never was down there. Because she was stuck at home, her battery had died, she didn't have a way to work. And I don't know what I could have done, because it was first day of class, so it was really tough. But I took the battery out. I can't remember how we did that. Yeah, that's right. On that Thursday morning, I got up early. The battery place opened at 7, so I was there as soon after they opened the door at 7 as I could be, and I changed my battery. The first thing I asked them to check the battery and see if it was any good. We put the thing across it, and it wasn't off that much. Okay, the voltage was not that bad. But when he put it on another device, he found out one of the cells was dead. Okay, so it had more probably internal resistance than most batteries do, and that prevented it from providing what we needed. Okay, so the terminal voltage is not the same as the EMF. Now, this schematic is how they represent that EMF. Picture this as your battery, okay, the big dotted box here. Okay, it has a voltage across it. That's the EMF. That epsilon or whatever that is, that symbol there, that stands for your EMF. Here is the internal resistance of the battery, the little r, okay? The terminals are here. This would be the negative terminal, that would be the positive terminal. The current, direction a positive charge would flow if the positive charge flowed, is going in this way from positive to negative, high potential to low potential, where most things go, realizing, of course, the electron currents in the other way because those are negative charges. They go across a resistor here. All right, Sam's here. decided to grace us with his presence tonight. Okay. Just a couple things. One thing, I'll probably repeat this every time someone comes in, so sorry you have to hear it over and over. The Vice President sent an email that I saw last week that said, as of 5 o'clock today, any students that were not paid, or not fully paid, would be removed from the roll. I'm pretty sure all of you are paid, so I'm not worried about that. But if you know anybody, any classmates in other classes that are not paid yet, please let them know they need to take care of that immediately, if not sooner, and they need to get in touch with someone in the business office and or financial aid office and let them know what their plans are if they can't pay it immediately. Are they going to stay with the course or not? They're going to be removed from the roll, but if you get your extenuating circumstances before them, they may give you a little slap. I don't know. Can't guarantee that. Number two, and this is sort of related to that, but completely different. Okay. I had a student call me Thursday after we had met on Wednesday that she was planning to come back to class. So could I send her all the stuff? She said, I've been following everything on YouTube, so could I send her the stuff so she could catch up? And I emailed back and said, well, I actually talked with her on the phone. I said, it's a lot of stuff. She said, no, I've been keeping up, so I think I could do it. She had a really tough situation and actually had to leave town. But she said she'd be back today, but she's not here. So the trouble is, when I emailed her the stuff, I said, and by the way, the Vice President sent this email saying, if you don't complete payment by Monday at 5 o'clock, you're going to be removed from the class anyway, so please try to get your payment. So she had Thursday, Friday, Saturday, Sunday, and today. I don't know if she's completed or not. So anyway, several of you I have returned stuff to, right? Please don't let those be too visible because there may be some people turning stuff in like that. So just letting you know. Okay, continuing. This is the setup. That is the external resistor. That's the load on the circuit. And this is how you measure the voltage across it. Of course, as long as there's nothing in between B and C and A and D, then these voltages here and there should be the same. And what you measure across A to B is not the EMF, that's the voltage of the battery. You have some line loss there in little r. Okay? So the schematic shows the internal resistance of the battery is little r. The terminal voltage of the battery is delta V, that would be V sub B minus V sub A. And the delta V is the EMF, whatever that is of the battery, minus IR. Because this current here, going through that little resistor, is going to drop your voltage in the battery. Okay? Now, for the whole circuit, the EMF is I capital R plus little r, okay? Because these two are basically resistors in series. So it's the current times the sum of the two resistors. Now, in reality, most of the time this large R is a great deal larger than the little r. Hugely different. And when that's the case, the little r is basically negligible. Okay? But it's not completely zero. Ever. Okay? All right. The internal resistance, and EMF continue. The EMF, and by the way, it's HAM. EMF used to stand for electromotive force, but they don't use that term anymore, but they still use EMF. Okay. It's not a force, it's a voltage. It's energy per unit charge. Okay, work per unit charge. But they still use the symbol little e or epsilon, and they call it EMF, though they never say what that stands for anymore because it's not a force. So E, or epsilon, is equal to the terminal voltage when the current is 0. So if you have no current in the system, you place your voltmeter across the terminals, there's no current there to speak of, then the EMF is 0. That's also called the open voltage circuit. That would be what you would measure there. But when you put a resistor in the load resistance, then the current is, a current does start, and when the current moves, then your little r resistance comes into play. The current depends on both the resistance external to the battery and the internal resistance of the battery. So both of those matter to E. But what you measure across the battery takes into account the internal resistance. And usually we really don't care what the internal resistance is. So when this capital R is a great deal larger than little r can be ignored. Generally, that's assumed in the problems. Okay? Now, your power relationship, I times E, that's your current times the internal resistance, that's the voltage. Okay? And that's equal to I squared R plus I squared capital R plus I squared little r. Now, this is correct. Current times voltage is power, so they have this right. And that is, another term for power is I squared R. And so I squared R, capital R plus I squared little r. And again, when capital R is a great deal larger than little r, most of the power delivered by the battery is transferred to the load resistor. Very little is lost in the internal resistance, if that capital R is large enough. Okay. The current in a circuit depends on the resistance of the battery. The battery cannot be considered a source of constant current because it varies, okay, because of that internal resistance. The terminal voltage of the battery cannot be considered constant since the internal resistance may change. The battery is a source of constant EMF, but not a source of constant terminal voltage. Okay? But once the resistance of the system is large enough, then the difference is very, very, very minor. Okay? Now, before we get to resistors in series, let's do a quick quiz. 2 quick quizzes, in fact. True or false? While discharging, the terminal voltage of a battery can never be greater than the EMF of the battery. When discharging, the terminal voltage of a battery can never be greater than the EMF of the battery. True or false? Okay. Terminal voltage can ever be, okay, here is the terminal voltage here, IR. It can never be greater than this because you always have a little bit of loss here. Okay, when it's discharging. Could be equal to if there's no current, okay? And this is topic 18, and that is indeed true. Okay? Number 18.2, quick quiz. Why does a battery get warm while it's in use? Have you ever noticed that? Okay, why does it get warm? Say again? There's current going through it, but current alone wouldn't make it warm unless there was resistance in it. So yeah, that's indication that the battery does have some internal resistance, okay? And frankly, the warmer it gets, the resistance actually goes up a little too. So the internal resistance may not be completely constant. All right. Now we go to resistors in series. I was thinking we did this in the Ohm's Law chapter, but evidently we didn't. So sorry, I misstated it earlier. Okay? When two or more resistors are connected end to end, they are said to be in series. Remember when we did talked about capacitances? When you connect one to another to another to another, they were in series. Same thing with resistors. Now, if you picture that, then the current leaves the battery, goes through the first resistor, the next resistor, the next resistor, as many as you got until it goes back to the battery. Well, guess what? There's only one current. There's only one loop. So the current is the same in all resistors because any charge that flows through one resistor has to flow through them all. Okay? Resistors don't use up charge, they use up the energy of the charge. Okay? Now, this is when you have in series. The sum of the potential differences across each resistor, that's equal to the total potential difference across the combination. In other words, the total potential difference across the battery. So every time you have a resistance, you know the current going through there, you know the resistors, I times R by Ohm's law is equal to the voltage drop. And then you go to the next one that drops again, the next one that drops again. By the time you get to the end, the sum of all these voltage drops has to be the voltage difference of your battery, or EMF, or power source, or energy source. Okay? Now, here's a couple of illustrations of this. These two lights are said to be in series because the same current that goes through the first light has to travel through the second light and back to the battery. So this would be your actual circuit. Does anyone remember the old Christmas tree lights? That if one light went out, the whole string went out. Okay? They don't build them like that anymore, I hope anyway. They build them in a strange little parallel method, but it does work. Okay? So, this is called those two resistors in series. And here's Megan, right? Yeah. Okay. See the back of your head. Okay. All right. I'm pretty sure this doesn't apply, but I need to say it because the Vice President said to say it. Okay. I'm supposed to read the script. I forgot to print it. Or when I saw the email, I didn't have it connect my computer to a printer, so I couldn't print it. And since I've been here today, I haven't had any time to sit down at my desk and print anything. So, just wanted everyone to know that after today, in fact, after 5 o'clock today, supposedly all non-paid students or people who had not completed their financial obligations to the system were or going to be or have been removed from the system. Hopefully that doesn't pertain to any of you, I'm pretty sure it doesn't, but if you know of anyone that may not have completed payment for some reason or another, be sure they get in touch with someone in the business office or financial services or somebody right away, if not today, first thing tomorrow, as soon as they can, because they've probably already been removed from the system. But if they want to be back, they need to let someone know what their plans of making payments are. Okay? And I'll start it again. Okay. Good to have you. Brianna's here. Okay, we've got everybody but FA, but she's on a mission trip this week, right? She's out of town this week. But two things. I'm required to say this to all students, so that's why when you came in I have to repeat it again. The Vice President sent out an email that I saw last week, but it was after this class was over with, that as of 5 o'clock today, all the students who were non-paid and not completed payment for the term were going to be removed from the system. Now, I think most of y'all all, but I think Shakina here are from other schools, right? How long before they remove unpaid students from the roll at your school?
First day.
First day of class?
Yeah.
Yeah.
First day.
Yeah. I had one student this morning say it's about the first week. They give them a grace period of a week. It's almost midterm. Thursday is midterm, and they're just removing non-paid students from the roll. So, if you know of anyone who hasn't completed payment, please have them get in touch with someone in the business office the soonest possible they can. Possibly someone in financial services, someone somewhere, and let them know what their plans are, if they're going to stay in the course or not. And if they're going to stay in, they're going to have to pay right away, very, very soon. So that's the first. Number two, I have returned some of your work to you, right? We may have a student who was here early in the term, never came to this class. She added this class late, but never came here. She may be coming to class. She emailed and called me on the phone on Thursday and said she was planning to be here. So please don't let the work that you've been returned be too visible, because otherwise you'll see correct that. Well, you understand that. Okay, so this is an example of two resistors in series with a voltage source. Okay, here's how we draw that schematically. The battery is represented, if you haven't already gathered this, if I say it, a long line parallel to a short line. The long line is always considered the positive pole, the short line the negative pole. Across there you have your voltage drop, the delta V, potential difference between the high potential and low potential side of the battery. Okay? The current flows through the wires in one direction. We always use conventional current, which goes in the direction of positive charge, would move if you had moving positive charges, which you usually don't. Okay, but that would be your direction of your current. Then your resistors are in series with each other. If the same current goes through this one, goes through that one, and comes back to the battery. Okay? Now, on such a system as this, two resistors in series, what you can do is just add the two resistors together and treat it as one resistor. In other words, we call that the effective resistance is the sum. They call it equivalent resistance. Is the sum of the two resistors when they are in series, not otherwise. The potentials add. Voltage drop across the first battery would be I times R1. Voltage drop across the second battery would be I times R2. It's the same I. It's a series circuit. It can't be but one current. But there's two resistors. You add the resistors together and get their equivalent resistance. The consequence of conservation of energy. You cannot, and also conservation of current, conservation of charge. I shouldn't say current, charge. The equivalent resistance has the effect on the circuit as the original combination of resistance does. So that equivalent resistance is the sum of the other two when they are in series. Okay, does that make sense? All right. If you had more than two, the equivalent resistance, now these are all in series. The equivalent resistance would be R1 plus R2 plus R3 plus R4, as many as you have going down the line. Okay? The equivalent resistance is the equivalent resistance of a series combination of resistors, is the algebraic sum of the individual resistances, and is always greater than any of the individual resistors. It's got to be, right? You're adding all the other resistors to it, so the equivalent resistance is always greater than any of the individual resistors. If one element in the series circuit fails, the circuit would no longer be a complete circuit, and therefore none of the other elements would work. Right? Remove one bulb, all the rest of them go out. Go back to this picture here. If you unscrew this bulb, there's no way for the current to get from this point to that point because it's going through the filament in that bulb to get back here. Yes?
So on that Christmas tree example,
Yeah.
if you take that bulb out and then connect the wires, will it work again?
It would if you knew which bulb it was. That's the problem. You never did it, I take it. I can remember my dad doing it. When we'd get them out the first of the year, plug them in, they wouldn't come on. Then he'd have some new bulbs, hoping they were working correctly. And he'd start with the first bulb, remove one, and then he assumed this one was good. So he went down and did that, and that one, and that one. And if you're lucky, one of them finally came on. Then that last bulb you took out was obviously the bad bulb. But if you got all the way to the end and it still didn't work, then you had to assume you had another bulb out. So then you went to the second bulb, got another new bulb put in, and went down the line again and hoped you got it. It was a pain in the neck, or some other body part. I don't know which. Okay, so it was really a mess. And then once they were on the tree, if one went out, then you had to do that all while they're on the tree, and that's even worse. Okay. Good question. All right. Now here's an example. This is example. Wait. Before I get to the example, here's two more quick quizzes. Yeah. This requires a picture. And how many of you have books or do not have books? Several of you do not. So let me see if I can draw this. It's not going to be pretty because I don't have much room to draw it. And my drawing stinks anyway. Okay. I'll draw it here. In this figure, I'll draw it down here, I think. Let me get my pen activated darkly. Okay. Here we have, what's that symbol for? Say again? It looks like an equal sign, but it's not. It's in a circuit. What does that symbol stand for? One short line, one long line. I just went over it. Okay. What if I said the long line was on the high side and the low line's on the... That's the battery, okay? Your potential difference. That is what you the symbol for it. The long line is the positive side, the short line is the negative side. Okay, the low potential side. Okay, now what we've got going here is you're going to run into an ammeter here. Okay, then you're going to run into a resistor here. This is R1. Okay. Now we run into another sort of strange situation here. You're going to run into a switch here. And right now the switch is closed. Okay? But above the switch, we have another resistor. Okay? So this switch is closed right now, but it is a switch there. And this is R2 here. Okay? Now, in that figure, okay, the current is measured with the ammeter at the bottom of the circuit. That's what the A is, the ammeter. When the switch is open, does the reading on the ammeter increase, decrease, or not change? This is not quite fair to ask you this now, but they're asking. Okay? You start with it like this. You read a reading on the ammeter. When you open the switch, does the ammeter read a larger number, a smaller number, or no change in the number? It's reading current. A is increased, B is decreased, and C is not changed. What you think?
So before it's going through the other resistor,
Say that again.
before you flip the switch, it's going through the other resistor.
Okay, good question. That's the key to it. When the switch is closed, we assume no resistance here. Okay? It's just like a complete circuit here. So therefore, I say this a little bit tongue-in-cheek, but maybe not totally, that current is a lot like students. It follows the path of least resistance. Not fair, is it? Okay? What I mean by that is going to find the easiest way to get around the circuit. With this closed, the current is going to come through here, and that's what the ammeter is going to read, go through R1, can't avoid it, and then because there's no resistance this way, and there is a resistance this way, it's going to go this way. So for a given voltage here, that doesn't change. And a given resistance here, that doesn't change. Then the current that you read here is the delta V divided by R1, right? So that's going to be a certain current. Let's call it I1. Okay? Open the circuit here. Open the switch here. And what happens now? The current can't get through here anymore. So it has to go this way, through R2. What does that indicate? The current has to go through the ammeter, through the resistor 1, through resistance 2, and then back to the battery. These two resistors are now in with this open. They're now in series. So the equivalent resistance is just increased. With the same battery here, same voltage across the battery, same delta V, potential difference here. Now your resistance is increased, your current has decreased. So the ammeter goes down. That should be B. So 18.3 should be B. I don't think, did I check the answers on the other? I guess I did. Yeah, 18.3 is B, sure enough. 18.4. The same circuit in figure 18.5 consists of two resistors, a switch, an ammeter, and a battery. When the switch is closed, the power, and that's P sub C for closed, is delivered to the resistance R1. Okay? When the switch is open, which of the following statements is true about the power PO, meaning the power when it was open, delivered to R1? Is PO greater than PE? No, PC. Is PO equal to PC, or is PO greater than PC? Power greater when it's closed. Okay? Now, on this one, I would refer you back to okay, does everybody see the circuit here? Okay? Does everybody see the circuit here? Okay? Now, the way I have it drawn now, the power through R1 is called PC, power closed. When you open the switch and it the current has to go through R2, that will be PO, power open, through R1. If you go back to this, I thought it was going to be right. It's pretty close to this one, okay? We're going to call it IV, okay, I delta V. That's going to be the power across the battery is I squared R1 plus I squared R2, okay? I'm sorry. Okay? That's when it goes through both, and I delta V is equal to just I squared R1 when there's, this is P open and this is P closed. No, I'm sorry, I got them backwards. Okay, this is P closed, and this is P open. Okay? Now, the difference here, though, this is I closed, and this is I open. This is I squared open, I squared open. Okay? What we're comparing is this term to that term. You see what I'm saying? We're looking at the power across R1 with the closed, as opposed to power across R1 when it's open. Okay? Now, which you think is the greater I? The R1 is the same in both cases, right? Is IC greater than or less than IO?
Can you repeat that?
Is IC greater than or equal to IO? Not really. Because you see your current, as you add another resistor with the same voltage, you double or increase the resistance, so the current goes down.
I was going to say less than, but you took away the option. So that's why I said, is it not less than?
No, I said, is IC greater than or less than IO?
Oh.
You said it was equal. IC would be greater than IO. Because, and therefore the power drop would be greater across the closed than it would across open. So going back to that picture, P, we call it P closed is greater than P open, so in other words, P open is less than P closed. That should be A. 18.4 is indeed A. All right. Now we're ready for the equivalent resistance example. Okay, series example. 4 resistors are arranged as shown here. You have a 2 ohm resistor R1, a 4 ohm resistor R2, a 5 ohm resistor R3, and a 7 ohm resistor R4. Okay? The A part of the problem says find the equivalent resistance of the circuit. Equivalent resistance of the circuit. How would you do that? How would you do that?
The equivalent resistance of the circuit.
Right.
Are they all in series?
Yep.
I just add them together.
Add them together. So you get 2 plus 4 is 6, plus 5 is 17. No, 6 plus 5 is 11, plus 7 is 18. Yes, they showed you right there. That is the equivalent resistance. Okay? Now, that's the A part. They basically showed you already. The B part. The current in the circuit, if the closed circuit terminal voltage of the battery is 6 volts, as listed here. What would be the current in that battery, in that circuit? Y'all did the lab in Ohm's Law, didn't you? How does Ohm's Law go?
Hold on, I'll got it. 3.
Not quite. How does Ohm's Law read? Y'all did the lab on Ohm's Law. What was Ohm's Law?
It was the I is equal to V over A.
That's it. I is equal to delta V over R. Right? You got your delta V, 6.0 volts. Yeah, you multiplied, you didn't divide. Well, yeah.
I divided 18, that's it.
Yeah, right. Rather than 6 by 18. So you had a reciprocal of it. Divided by 18.0 ohms. And that would give you 1/3. 1/3 of an amp. If you wanted to write that as a decimal, that would be approximately 0.33 amps. Or you could have called that 330 milliamps if you wanted to say that. However you want to say it. Okay, so there is the B part. 0.33 amps approximately. Okay? Now, number C. Calculate the electric potential at point A if the potential at the positive terminal is 6 volts. What is the potential at point A? Point A, you see, is right up there, right between R1 and R2. What would be the potential at A if the battery is at a +6? Okay. What does Ohm's Law say?
We're looking for the delta V.
Yeah, the delta V, actually just the potential V at this point. That would give you the delta V between those two. So what would the potential need to be there? You've got a current, you just told me, you know the resistor. What does Ohm's Law tell you?
It would not be 0.
No, it wouldn't. Usually you count the negative side as being 0, so this is plus 6 over here. Now, if those other 3 weren't in there, then A would be at 0 because it would be the same as negative.
So are you using the other 3 resistors?
Not at all. You could if you wanted to. It makes it harder.
1.65.
What does Ohm's law say?
It says you have to divide the
What are you looking for?
current by
What are you looking for?
the voltage.
Voltage. What does Ohm's law tell you voltage is? That's 6 down here, not up there. What does Ohm's law tell you?
It's the current times the resistance.
Okay. And you know the current?
133.
Okay. And you know the resistor?
2.
Multiply those together?
2/3.
2/3. So therefore the potential here would be 2/3 less than the potential here. So 5.3. Right? And it drops more when it goes there. It drops more when it goes there. It gets down to 0 by the time it gets here, wherever you are there. You see? You have a voltage drop across the resistor, so that potential should be at 5.3 volts. Okay, at A. That was the C part. The D part. Suppose the open circuit voltage, or EMF, epsilon, is 6.2 volts. So you have here the okay. In other words, that this, the 6.0 volts is the voltage across the battery, but this in here is actually 6.2 volts. Okay? Calculate the battery's internal resistance. So we're looking for the little r here. What would that be? Okay, how'd you get that? Say again?
Current divided by the voltage.
What voltage did you use? Okay. Don't think that's 1 because you see 6 is now from here to here, the positive pole of the battery to the negative pole of the battery. The EMF is 6.2, so you have a voltage drop here of 0.2. That's the voltage drop across here. The current across there is, you're saying, 0.33. I is equal to 0.33 amps. This is, okay, divide this by that, and what do you get? Divide 0.2 by 0.33, is that what you get? Zero point what? 606. Is that what you said? Okay. Okay. So about 0.6 ohms. Is that what your answer was? And that's what they got in the book too. Very good. You see why? And how? Okay. That was the D part. The E part. What fraction, F, little f, of the battery's power is delivered to the load resistors? Okay. Now, in that case, that we're counting internal resistors, these are the load resistors. It said what fraction? F. The numerator for the fraction is going to be the amount of power delivered to the 4 resistors, or to the 1 equivalent resistor, right? The denominator is going to be that associated with the 6.2, right? Okay. Now, as we were just doing a little bit before, your power across the big resistors is I squared R. And we'll use the equivalent resistors here. Why not? One measure. Okay? Your power produced by the battery is I epsilon, current time voltage. So 0.33, your current, times 6.2, what would that be? 0.33 times 6.2. Say that again. 2.046. Okay? That would be watts. Okay? I times E. That seems reasonable. Okay? What would be your I squared R there? That's 0.33 squared times 18. Say that again. 10.3? Okay. You do 0.33 squared.
Oh, squared. Oh.
Times 18.
1.96.
1.96 watts divided by 2.05 watts. And what fraction would that be? 1.96 divided by 2.05. Pretty large percent. 0.95? 0.952. So approximately 95%. Okay? See what they got? They said 97%. And what they said yeah, okay. I guess it's round off error. So what they did say was delta V over E is going to be that same percent because the I is the same in both cases. So 6 divided by 6.2. What does that give you? .96. Yeah, 6 divided by 6.2. 0.967. So that would round to 97. Or 0.97. Written as a percent, it would be 0.97. Yeah, that's what they got. Okay. Good deal. Now let's look at resistors in parallel. Now what do we mean by that? You got resistors, you got a resistor here, and here, and here, and here, but they're not connected to each other. They're just all connected to the battery. They're in parallel. The potential difference across each resistor is exactly the same because each one is connected directly across the battery terminals. The current I that enters a point must equal the total current leaving that point. So they don't have a figure here yet, but if they had two resistors, and I going through one resistor was I1, through the other was I2, they split that way going out and come back to that way coming in, so I is equal to I1 plus I2. The currents are generally not the same unless the resistors were exactly the same. Consequence of conservation of charge. You can't make up charge or throw away charge or lose charge. Charge is conserved. Okay? So here is your parallel circuit. Your positive pole of the battery is connected to the positive pole of the first light, also to the positive pole of the second light, and the negative pole of the second light is connected to the negative pole of the first, and that's connected to the negative pole of the battery. These two bulbs are in parallel with each other. Okay? And here's how we draw them schematically. Again, we took the battery here, delta V. What's the symbol for a battery?
One big line and a little.
Yeah, two parallel lines, one large, one small. What does the large one represent? The symbol for a battery.
Oh, the larger one represents the
Positive terminal, which is the higher potential, and the negative is the low. The short one is the negative side of the low potential. Okay? So you have a delta V from the battery. The current goes up here, but at point A, the current splits into I1 and I2. I1 goes to R1, I2 goes to R2. So at this point, I1 plus I2 equal I. I1 goes through R1, I2 goes through R2, and then I1 comes out of R1, I2 comes out of R2 at B. They combine back together, and again, I1 plus R2 is equal to I. Goes back in. Okay? The voltage across this resistor is delta V. The voltage across that resistor is delta V. So the voltage across each one is the same. The current typically isn't if those two resistors aren't the same. Okay? Now, what is the equivalent resistance here? If they just give it to you, I can't remember if we did it in the last chapter or not. I guess we didn't. I don't recall. I thought we did. But with parallel resistors, the equivalent resistor, the inverse of the current equivalent resistor, of the reciprocal of the equivalent resistance, 1 over Req is equal to 1 over R1 plus 1 over R2, as many as you have out there. Now, what's the ramification of this? Equivalent resistance replaces the two original resistors. Okay? The household circuits are wired so that the electrical devices are connected in parallel. Why would we want to do that? In a household circuit, why would we want the circuits wired in parallel? The devices, electrical devices, wired in parallel. Any idea? Well, name some household electrical devices. The toaster. Okay? Now, what's that toaster typically designed to operate at?
That's how high up you put it.
What you mean? How on the shelf you put it? Okay. What do you think? 120 volts?
Maybe less.
Maybe less. Yeah, it could operate less. Okay, name another common household electrical device. The refrigerator. Okay? Let's say the toaster and refrigerator are in series with each other. Not parallel, but in series. So, you have 120 volts that they're plugged into, and then when you go to the toaster, you drop a voltage there, and then a refrigerator drops a voltage there. Neither one of them can possibly be at 120 volts. Yeah. So more than likely, they're not going to operate too well. Okay? Because you would have to boost the voltage then to get them plugged. And then one would probably be operating a higher voltage than it needed to be, and the other lower, or something like that. So that's one reason. The other reason is, what if you flip the toaster off so no more current was going through it? Yes. Let's see. What is it? Hour and a half in? Yeah, 7 now. Yeah, we're not nearly at the place to do a lab yet, so it looks like not. Yeah, I can. We wait till we have sort of a break that time. Yeah. Okay. All right, where were we? Okay, what were we saying? Yeah. So let's say you turn the toaster off, so no more current was flowing through it. What would that do if that was a series circuit? What would that do to the refrigerator?
If it was in a series,
Yeah.
it would make the refrigerator not work.
Exactly. It would turn off the refrigerator too, because if you open the circuit on the toaster, then the refrigerator couldn't get any juice, right? So no, that wouldn't work at all well in electrical devices in your home. Okay? They are connected in parallel. Okay? Now what's a hazard with that?
The wire can catch on fire and burn the house down.
Why?
Too much current going through the wire.
And why is that? Because the currents add. And the more things you put in in parallel with them, the more current has to be produced. Okay? And you're absolutely right. You could melt or burn up the circuit because too much current would be going through that wire. Especially if you had, say, the toaster and refrigerator wouldn't be too bad in parallel, but I wouldn't want to put too many more things in parallel. Especially things that drew a lot of current that would then make this I total much greater than before. Now here's the thing to note here. Give me a resistance for R1. Just make up one. 100 ohms, right? Okay, so R1 is 100 ohms. Okay? What's R2? Give me a one.
100.
Oh, come on, something different.
200.
200, okay, so the R2 will be 200 ohms. What's the equivalent resistance then? Just make up something you think would be close.
150.
150. Let's see what it is. 1 over REQ, okay, is equal to 1 over 100 plus 1 over 200. Okay, on the right-hand side, what you need before you can add those. What the same? The denominator. So what would you need to do to the 100? Multiply it by 2, but you'd have to multiply the numerator by 2 too, right? So this would be 2 200ths plus 1 200th would be 3 200ths, right? And that's 1 over REQ. Now, how would you get EQ?
Cross multiply.
You could. It's even easier to flip them, right? Right? So that would be 200 divided by 3. Same thing you get if you cross multiply. 3 REQ is equal to 200 divided by 3. Okay. 200 divided by 3.
66 and 2/3.
66 and 2/3 ohms. What do you notice about that? Not nearly 150. In fact, it's less than the least of those. And that's the key. Okay? Because the more things you put in parallel, the greater you drop in their equivalent resistance, the greater current you're having to supply with that same delta V. Because your equivalent resistance is less and less and less. The more things you add, it gets less and less and less. In fact, not only that, it has to be less than the least of those individual resistors. So if one of those would say only 10, then that drops your equivalent resistance to less than 10 automatically, without that. Okay? So circuit breakers may be used in series with other circuit elements for safety purposes. Yeah, you're wanting to measure the total current going through the system, and you want that circuit breaker to break the circuit before you get too much current. So yeah, you want those in series with the other circuit elements. Otherwise, it wouldn't do you much good. All right. So equivalent resistance in parallel, we just were talking about that. 1 over REQ is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1, as many resistors as you have. Okay? The inverse of the equivalent resistance of 2 or more resistors connected in parallel is the algebraic sum of the inverses of the individual resistance. Blah, blah, blah. The equivalent is always less than the smallest resistor in the group, whereas in series, the equivalent resistance is always greater than the greatest in the group. Okay? So, this one that they showed here we have an 18-volt battery here, pretty strong battery. What you usually use on tractors, I think, are 18-volt batteries. Okay? What would be the equivalent resistance of these 3 resistors in parallel? Notice every one of these is 18 volts across it. So what's the equivalent resistance? 1 over REQ is equal to 1 over 3 plus 1 over 6 plus 1 over 9. What you got to do?
1.64.
Second?
1.64.
Okay, the equivalent resistance is 1 point, wait, I'll write it this way. REQ is equal to 1.64. That sounds reasonable. I haven't checked it. It's less than the least of those. Okay? Now, let's check it another way. What would be the current across this resistor? I1.
I always forget to do multiply.
Okay? Name Ohm's law for it. 6. It would be 6. Okay? So I1 would be 6. How about I2? 3. I3 would be 2. These are all amps. That's a lot of current, by the way, but okay? Not a very realistic thing. What would be your total I? Say again?
Do you add the,
Yes, you do, because you see at this point, splits 3 ways. So, say again?
it'd be a lot.
Not a lot. 6 plus 3 plus 2. 11. 11 amps, right?
I was thinking you add the resistor
No. You,
and do it.
No. We calculated with these resistors, now you add the currents. Currents add, resistance don't. Resistances add in series circuits, not parallel. Okay, we already calculated the equivalent resistance. Okay, so since you have 11 amps being produced by an 18 volt current, what would that give you as the effective resistance? Req would be, well, how would you get it? 18 volts divided by 11 amps, and see if you get it that way too. You should. Is that how you did it before?
No, I did it.
Yeah, well then try it this way. We're just checking our answer. It looks right, but I want you to check it. Exactly, right? 1.64 ohms. Very good. That way we confirm we were doing it right. Okay, we just did example 18.2. Probably before we did that, we should have done quick quiz 18.8. So let's back off and do that. Okay, 18.5 and 18.6. Okay. I'll draw the circuit here. What's that the symbol for?
Battery.
Good. Which is plus, which is minus?
Longer is positive.
Okay, and the short is negative. Okay, and we leave there. And we go up to a place where you have a branch that goes up to a switch, which starts off being open through a resistor, R2, and then coming down and going back out to close the circuit. And on the lower side of that, we have a resistor, R1. Okay. This just jumps around. Oh, I left off something. Let me, of course, when I do this, it's going to erase way too much. Okay. Okay. Comes out here, goes through an ammeter, and then comes back home. Okay. Actually, it goes out through the ammeter. Doesn't really matter where you send it. All right. There's the setup. In this figure, the current is measured with the ammeter on the right side of the circuit diagram. Okay, who cares? When the switch is closed, does the reading on the ammeter increase, decrease, or remain the same? So it starts off being open. When you close that switch, does the reading on the ammeter increase, decrease, or remain the same?
Decrease.
Why?
Because when you close it, it's going through 2 resistors.
It's going what?
When you close it, it's going through 2 resistors.
Through 2 resistors, but in what way?
Parallel.
Parallel. And the second resistor actually lowers the effective resistance. Or the other way to look at it, what the ammeter reads right now is this voltage across that resistor, right? Okay, that's going to be your I1. When you close that, then you still have that same I1 across this one, plus you have I2 through that. And I1 plus I2 is certainly greater than I1, right?
So it makes it higher?
It makes the current higher, yeah.
Um,
Is that not what you said? I thought you said increase.
yeah, that's
Okay. And that's absolutely right. Because the effective resistance with two in parallel is less than the least of the two resistors. Okay? So that should be an A increase. 18.5 should be A increase. It is. 18.6. When the switch is open in this figure, the power P0 is delivered to resistor R1. Okay? So when the switch is open in this figure, P0 is given to R1. Okay? Is delivered to resistor R1. When the switch is closed, which of the following is true about the power PC delivered to R1? Not R2 or the R1. Okay? Neglect the internal resistance of the battery. Okay, the A says PC is less than PO. B says PC is equal to PO. And C says that PC is greater than PO. Which of those is true? Power delivered to the R1 when that's closed, is that greater than, less than, or equal to the power delivered to R1 when it's open?
power is greater when it's closed.
Why is that true?
Because power is based on the current,
Okay,
and the current's higher when it's closed.
the current is greater where?
When it's closed.
Greater where, though?
Oh,
I agree if you're talking about down here. Through the ammeter, if the current is greater. We're talking about the current through R1.
when it's closed or open.
Both, either. There's a change in it between the time R2 is open and closed. Power. If it does, is it greater or less?
It is less.
I contend it's equal. Because this voltage is across R1 now, right? When you open, when you close that, the same voltage is across there, the same current flows through there, so the power is the same. So I say this is across R1,
But the resistance changes.
not through R1. It said through R1, power through R1. Because the current through R1 doesn't change. Because this is in parallel, that voltage is across that resistor, producing I1, and I open and I close are exactly the same through R1. Down here, through A, no. Sure enough, when you close that, A goes up. But across here, A stays the same. I mean, not A. Yeah. I stays the same. Okay? So I think that one should be B. 18.6 should be B, and it is. Okay? Now we go back to this one. Okay? Three resistors are connected in parallel, shown here. Potential difference 18 volts is maintained between points A and B, shown there. Find the current in each resistor. We did. 6 amps, 3 amps, and 2 amps. 6 amps, 3 amps, and 2 amps. Very good. Calculate the power delivered to each resistor. The power delivered to each resistor. What would that be? We'll call this P to resistor 1. What would that be? What is power?
$108.
108, you said? Yes. Well, wait. Yeah, right. 6 times, yeah. It's current times voltage. And that would be 108. What units?
Watts.
Watts. What? Watts. Okay, got it. How about through R2? More like 54?
Yeah.
Okay. It's exactly half that, so it would be half the power. P through 2 would be, 54 watts. And P through 3, that was your 36. So P3 would be 36 watts. Okay? Whoa. Wrong, eh? Okay. Okay, no. Okay. They rounded the 108 to 110 because they had 2 significant digits. Really picky, okay? When I looked at that, I said, how in the world? But that's a round-off thing. And 54 and 36, yeah, exactly right. And they did it the hard way. They did I squared R. A lot of extra work. Just do I times delta V. Okay? And sum to get the total power. Add those 3 up. I would add our 3 up. 54 and 36, I'm pretty sure adds to 90. And 108 would be 198. Which they may round to 200 watts. Yes, they do. 2.0 times 10 to the second. Yeah, right. Okay, 200 is close enough. All right, did that give you everything? Equivalent resistance. Oh, wait, do we do equivalent? Yeah, we did that. Okay. Find the current each resistor, power delivered, equivalent resistance we did, and find the total power delivered. Yeah, got it. Equivalent resistance 1.6, they didn't do 6.4, and then the second one, they wanted you to do the power dissipated by the equivalent resistance, and if you did 18, you V squared over R, so 18 squared divided by 1.6, hopefully you get the 2.020, 200 like we did before. Okay. Tip 18.2. Well, let's see, they may show this on the slide. I think we already read all this, didn't we? The inverse of the equivalent resistance is connected in parallel is the algebraic sum of the inverses of the individual resistors. The equivalent resistance is always less than the smallest resistor in the group. We said that. Okay. No, they don't do tip 18.2. Don't forget to flip it. When you do the reciprocal plus the reciprocal plus the reciprocal and add those together, don't forget to reciprocate the answer as well. That's what they're saying there. The most common mistake in calculating equivalent resistance for resistors in parallel is to forget to invert the answer after summing all the other reciprocals. Don't forget to flip it. Okay, quick quiz 18.7. I wish y'all had your books because this one is quite long to read. Suppose you have 3 identical light bulbs, some wire, and a battery. You connect one light bulb to the battery and take note of its brightness. Okay? You add a second light bulb, connected it in parallel with the previous light bulbs. Only one light bulb. And again, note the brightness. Repeat the process with the third light bulb, connecting it in parallel with the other two. As the light bulbs are added, what happens to A, the brightness of the light bulbs? What do you think? You got one light bulb across the battery, and you do another one in parallel with that, and then another one in parallel with that. What happens to the brightness of those bulbs? No, they stay the same, because you got the same voltage across each one, and they're identical light bulbs. Okay. Now, they won't stay the same for too long, because you're going to run that battery down pretty quickly, because you're having to supply the current for 3 light bulbs now rather than just one. Okay? So, the brightness of the light bulbs should stay the same. Let's just check it and make sure they got that right. Parallel, unchanged. Right. Okay? B, the individual currents in the light bulbs. The current across light bulb 1, the current across light bulb 2, the current across light bulb 3. What about them? Okay, they are the same, because you have the same voltage across identical resistors. Okay? So that stays the same. Okay? Unchanged. Okay? C, the power delivered by the battery.
That won't stay the same.
That what? I couldn't hear.
I was going to say it won't, but I picked wrong, so will it change?
It increases big time, because now you've got the same power, 3 times the current. So the same voltage, 3 times the current. So you got 3 times the power delivered by the battery. It can't sustain that too long. It says here, increase. Okay? And then D, the lifetime of the battery.
That will
It'll use up really quickly, so that decreases. And sure enough, that decreases. Now, let's do 18.8. If the light bulbs in Quick Quiz 18.7 are connected 1 by 1 by 1 in series instead of in parallel, what happens to the brightness of the light bulbs? So you have the battery here, you do one bulb, another bulb, another bulb. Same circuit. What happens to the brightness every time you add another bulb?
will that decrease?
Decrease big time, because you see the voltage of the battery, that doesn't change. You put one light bulb across it, it's the same as one light bulb before it. Then you put a second in series with it, now the voltage gets split. Half the voltage here, half the voltage there. The current decreases, so they get dim. Okay? Put a third one in, it gets even dimmer. We're going to do that in the next lab. Okay? So the brightness of the light bulbs decreases. So 8 is decrease. The individual currents in the light bulbs. That's a decrease.
They'll decrease.
Because one bulb has just one resistance, the potential difference here, so that gives you a current. Put a second in series, the battery is the same, but now you got 2 resistances, add those together, the current has a decrease. Put another one in, it has a decrease some more. So the current decreases every time you add another bulb, and that's decrease. Okay? Number C, the power delivered by the battery. Decrease too, because the delta V is the same, but the current has decreased each time, and delta V times I, that's power. So it decreases each time. Okay? And then finally, the lifetime of the battery. No, it actually increases.
The lifetime?
The lifetime of the battery, and why? Because what the battery produces, if you read how they rate a battery, they say amp hours. In fact, how much charge does it do? Well, you see, that all depends on the current. And if your current was decreasing, the battery isn't having to supply very many amps. It decreases each time, so it has so many amp hours in it, so the less amperage you have to create, the longer you can create it. Okay? So that actually increases. Good deal. Okay. Now, there's a couple of applying physics, and they show some light bulb combinations. And I wish that y'all had your books. I'm going to erase everything on this slide. Try to draw what they have here. Okay. Here we have the battery. Short line, long line. So this is the plus side, this is the minus side. And you go up here, and you go into, and this is the light bulb. How I'm going to show it as a light bulb is put a circle around it. So there's a light bulb. This is light bulb A. Yeah, they did it in the book. So here's another one. Okay, that's light bulb B. Okay, then you hit a line here. Ooh, yuck. I need to go back and adjust something. Okay. I have another light bulb here, and we'll call that light bulb C, that connects across there. And then I have the battery. Plus side, minus side. And then this connects over here, but you have another light bulb here, and this is D. Okay? Rather strange current there, circuit there. Says compare the brightness of 4 identical light bulbs, A, B, C, and D, identical light bulbs, shown in this figure. Okay, first thing we're going to compare the brightnesses of those bulbs. You tell me which will be the brightest of those 4. A, B, C, and D. D's over here. A's and B are up there, C's here, and D's up there.
They're all the same.
They're all the same bulbs, but they're not all the same brightness. B would be brighter? Huh?
D.
D. Okay. Afraid not.
What?
Afraid not.
C.
C would be brighter. Okay, and the reason is the potential difference across C is the potential difference across the battery. So you get a full amount of current here. The potential difference across A and B together is that across, so they have to split the bulb.
What about D? It goes through D.
Okay, take a look here. What's the potential difference across D? Where is the current going to go here? Through D or through here?
Oh, I didn't see that.
Oh!
I didn't see that line.
Yes. Okay? And you mean to call roll again? Okay, yeah. Okay. Got to call roll for lab. We aren't actually probably going to be able to start a lab tonight. Well, we might. We'll see. But, let's see. Okay. I have to stop and think. 5:30, 7:20, yeah. Yeah, so it is time to mark roll again. Tia is here. Megan's here. Shakina is mostly here. Courtney's here. Sam is here, and Brianna's here. Okay. Now, did y'all say you needed a break?
Yeah.
Okay. Now let's keep it really short because we got started late. Because of my last, let's keep it 5 or less.
Okay.
What's that?
Can I get my stuff out?
I can't hear.
My test score.
Oh, okay, yeah. Okay. Okay. All right. It's coming back up slowly. We are recording again. Okay. Now, remind me, which of these bulbs is the brightest?
C.
C. Dimmest?
A. D. What is it, D?
D doesn't even come on because you see the current goes through this way. It doesn't go through D at all because the current likes to follow the path of least resistance, right? Okay, so D doesn't come on. A and B are equal brightness, right? Okay, so the brightest is C, next to A and B are the same, and then D doesn't come on at all. So that's the first thing it asks. Compare the brightness of the 4 identical light bulbs shown in that figure. What happens if bulb A fails and so cannot conduct current? What happens to any of the other bulbs? If A fails, what happens to the others? What happens if A fails?
They did.
No, B goes out because B's in series with A.
So the rest of them are
No, C is not in series. C is in parallel with A. So C would stay on. D was out anyway. It doesn't come on. But B goes off. C stays on. Okay? All right. What if C fails? Nothing happens. A and B stay the same. D stays out. Okay? What if D fails? Nothing happens. D is not even a material, and it's off anyway, so what would it matter if it failed? Okay. There's another applying physics thing on a 3-way light bulb. And I don't know if this is all that worthwhile, but it is pretty interesting how they do a 3-way light bulb. And you have but I'll let you look at that. It's probably not worth my trying to draw. So let's move on to problem-solving strategies. And they say 1. Okay? So what we're trying to do is come up with basically effective resistance. Okay? Well, not. There's more to it than that. So the first thing, if you have any resistors in series, add them together and treat them as an effective resistance. Okay? They all carry the same current. The potential difference across them individually are not the same, but the resistors add directly to give the equivalent resistance of the combination. So for all those in series, just add them together. Draw the simplified circuit diagram just with their effective resistance rather than those in series. Okay? That's step 1. Step 2, combine all the resistors that are in parallel. The potential differences across them are the same. The currents through them are not the same. And the equivalent resistance in parallel combination found through that reciprocal relationship, 1 over R EQ is equal to 1 over R1 plus 1 over R2 plus 1 over 3. Remember to invert the answer after summing the reciprocals. Then draw the simplified circuit diagram with the equivalent resistance in it. Okay? Repeat the first two steps as necessary. A complicated circuit consisting of several resistors and batteries can often be reduced to a simple circuit with only one resistor. Replace any resistors in series or parallel using steps 1 and 2. Sketch the new circuit after those changes have been made. Continue to replace any series or parallel combinations. Continue until one equivalent resistance is found. They said it over and over and over again. Okay? Use Ohm's law. When you're finally get an equivalent resistance, use delta V is equal to I times delta R, I times R EQ to determine the current in the equivalent resistor. Okay? Start with the final circuit found in step 3. Gradually work backwards through all the circuits, applying the useful facts from step 1 and 2 to find the current in the other resistors. A lot of blah, blah, blah here, but it's really a lot simpler than it sounds. Here's an example. Okay? This, by the way, is example 18.3 on page 598. Okay? Now, well, they did it in the book too. It just seems like they did way too much here. Okay? What you have 4 resistors are connected as shown in the top figure. Okay? Here you have an 8 ohm resistor in series with a 4 ohm resistor, and then that is connected to 2 parallel resistors, a 6 ohm and a 3 ohm. Okay? And then you get to point C. So you start at point A, go to point B, and then end up at point C. Now, what are you going to do first? And you're trying to simplify this circuit. What do you do first? Add the 2 in series. That gives you a 12 ohm resistor, and that you treat that as that. Then what? You what?
I'm not, no, because it lights. And so
Okay.
it's sorry.
What do you do next? Okay. Well, these are 2, and you've got this to be the 12. Fine.
Oh, do you add those two?
You don't add them.
So turn.
You add the reciprocals, because these are in parallel. Okay. It's just a
Is that a force slide? Is that it lights?
No, please don't do
It's
that.
gonna bite you.
Oh my God.
okay.
It's on my back. Oh, it's gonna be in my back.
Okay. So what you do with these? We got that 12. How do you combine those two?
Something just tells me to do
So you divide
divide by 3.
Okay. Okay. You do 1 over 6 plus 1 over 3. Right? Least common denominator is
No,
6. Okay. So you make this 2 over 6, right? Okay. 1 over 6 plus 2 over 6 is? It is 3 over 6, which is 1/2. But then you reciprocate that and make it 2. So that becomes a 2 ohm resistor. Right? Now these 2 are in series again. So you add those 2, and that gives you 14. So that gives you a 14 ohm resistor. Okay? So the complex circuit combines the resistors in series. parallel, and these two are in series, so combine those, and we draw each circuit with the equivalent set. Combine the resultant resistors in series, and finally there's your equivalent resistance. Okay? Now that's all you had to do with that one, but let's see if there's something more here. Okay? Find the equivalent resistance. We got it, 14 ohms. Okay. What is the current in each resistor if a 42 volt battery is connected between A and C? So here we're saying at the end, let's connect a 42 volt battery. Okay, plus side, minus side. Okay. Okay. It says, again, what is the current in each resistor if a 42 volt battery is connected to between A and C? Can you tell me what the current would be through this? Yeah, 42 volts here, that's 14 ohms. 3 amps. You're absolutely right. Yuck. This would be a current of 3 amps. Okay? But that's just a defective resistance. Okay? If you have a total of 3 amps going from A to C, how do they split up here? You still have 3 amps here, but how about up there? Well, 3 amps through a 12 ohm resistor would be what? What voltage would you have across there? You know you got 3 amps. What voltage drop would you have across there?
4.
Okay. 3 amps times
Oh,
12
36.
is what? 36. Yeah, 36 voltage across here and
6.
6 across there. No, yeah, 6 across there. 36 and 6, sure enough, is 42. So that's working. So you have 36 volt drop across here. So you have to have that same 3 amps through here, 36 volts across the whole thing. So what would be the voltage drop across this one? If you have 3 amps here, that's the same 3 amps you have here, same here, 3 amps through those two.
36. Would you add those and multiply by
Okay, what would be the voltage drop across that?
24?
Right, 24, and this one would be
12.
12, and 12 and 24 is 36, so that makes sense. So, to answer the question, well, actually, we didn't need that answer. We asked what is the current through each resistor. 3 amps through here, and 3 amps through there. Okay? But this 3 amps here is split into 2 pieces. Part of it goes there, part of it goes here. The voltage drop here is 6 volts across here. So how much amps is going through here? 6 volts across here. How much current through here?
2, 3,
6 volts, 6 ohms.
36. 12. 12. 1?
1. Voltage divided by current.
Oh, 1. Oh,
Yeah,
okay.
is divided. And how much current goes through this one?
2.
2, exactly. So your final answer is how much through each resistor? 3 amps, 3 amps, 1 amp, and 2 amps. Because 1 plus 2 had to be 3, and that's what comes out here. So I think we've done exactly what it asked for there. What is the current through each resistor if that happens? That's exactly right. Okay? Now, Gustav Kirchhoff, okay? Good Irish name, right? Nah, probably German. Lived 1824 to 1887. What was happening over here about that time?
A war.
Yeah, we had the war between the states then, didn't we? So that's about the time period in which he lived. It was probably in Germany. He invented spectroscopy with Robert Bunsen. I wonder what else Robert Bunsen may have invented. Y'all ever done a chemistry lab? A Bunsen burner, of course, okay? But the two of them invented spectroscopy, in which they studied the wavelengths of light, as things are burning and stuff. He formulated rules about radiation, and he also came up with what we're going to be studying, rules for currents and voltages in a circuit. They're called Kirchhoff's laws, or Kirchhoff's rules. Some books call them laws. These are ways in which the resistors can be connected. And by the way, this is section 18.4. These are ways in which the resistors can be connected so that the circuits formed cannot be reduced to a single equivalent resistor. There are ways in which resistors can be connected so that the circuits formed cannot be reduced to a single equivalent resistor, like we did in the last example. Two rules called Kirchhoff's rules can be used instead of setting up those kinds of things like we just did. Okay? There's two rules. The first is the junction rule. That's a pretty simple one, and we've really been using it already. Okay? The sum of the currents entering any junction must equal the sum of the currents leaving that junction. Okay? You can't, this is a statement of conservation of charge, you cannot create or destroy charge. Same amount that comes in has to come out. The second of these is called the loop rule. The sum of the potential differences across all the elements around any closed circuit loop must be zero. That's basically conservation of energy. Okay? So those are the two Kirchhoff's rules, and we'll see how to use them. Okay? The first one, the junction rule. If you have I1 coming into this junction, and then it splits, what can you say about the relationship between I1, I2, and I3? I1 comes in, I2 and I3 go out.
The series of it.
Okay. I1 must equal I2 plus I3. Because you got one coming in, two going out, and some of these must equal that. Right? That's from the conservation of charge. The current I1 entering the junction must equal the sum of the currents I2 and I3 leaving that junction. Got to be equal. Okay. Think of this as water or air or something else. If you have a certain flow in here, but then you have a Y here, some of the air flow will go here, and some will go there, right? The flow in equals the sum of the flows out. Okay? Same type deal here. That's the analog, mechanical analog to the junction rule. The loop rule. Statement of conservation of energy. To apply Kirchhoff's rules, you assign symbols and directions to the currents in all the branches of the circuit. Okay? Guess what? If you assign a direction to the current and it happens to be wrong, does everything fall apart? No. It's just when you get to the end of the problem, it'll say that current's a negative current, whereas you assumed it was positive, it shows it negative. If the direction of the current is incorrect, the answer will be negative, but you have the correct magnitude. So you choose a direction to traverse the loops and record the voltage rises and drops. Now, what would cause a increase in voltage? there's really two things, maybe more, but two major things that will cause an increase in voltage. Second?
What's a hit?
Okay. Okay. Okay, there's a circuit. What's this a symbol for?
A battery?
Battery. That is a resistor. Pretty ugly, but it's a resistor. Okay? Now, this is going to illustrate both of the things I was going to say. That is a circuit loop too, right? Let's say you assume the circuit is flowing in that direction. A correct assumption, by the way. So therefore, when you are following along the circuit, pick a point to start with. I don't care where. Let's just start here. Assuming the current is flowing in this direction. We can name that as I. There will be your I. Okay? This is your delta V, and this is your R. Right? So if we're starting at this point and going around in this direction, the current's flowing that way, the voltage drops across here because what is voltage? Energy per unit charge. A resistor uses some of that energy. Okay? So therefore you have a voltage drop. So this would be a minus IR. Okay? Continue on around here, and here you have a what is the short symbol? Minus. The long one is plus. There you have an increase in voltage. So that you would have minus IR plus delta V is equal to 0. So you go back to where you began, and the sum around all that is 0. And that says delta V is equal to IR. That's Ohm's law, right there. Okay? Now, what if, for some mysterious reason, you had decided to make the current flow in the other direction? Like this. I mean, no, you do the loop around there. You still say the current is going right, but if you're starting at this point here, and you go down in voltage, if you're going across the battery in that direction, that's a minus delta V, right? Because you're going down in voltage. But then if you go this way, the current's coming this way, you're moving this way, that would be a drop in voltage across there, IR. But if you're going the other way, that's an increase in voltage, IR. So you have minus delta V plus IR is equal to 0. Move the delta V to the other side, you still got Ohm's law. Delta V is equal to IR. Okay, so that's what we mean. So if you had chosen it that way, that the current was going in that direction, then you would have been a minus here and a plus there. You would have come out with a negative I, and then you just say, oh, it's really shouldn't be a negative I, it's going the opposite way. And it would have done. I think when we see the more complicated circuits, you'll see that. Okay? But that's examples of an increase in voltage and a decrease in voltage. Across a resistor in the direction of the current is a decrease in voltage. Across the battery and jumping up, that's an increase in voltage. Going across the battery in the opposite direction is a decrease, and going opposite the current in the direction of your loop, that would be an increase in voltage. Okay. More about the loop rule. In traveling around the loop from A to B, now that's not really a loop, is it? It's just going across the Sorry. Okay? If you're traveling in this way from A to B, and you go across a resistor, and your current is moving in that direction, what is your delta V there? What's your change of voltage there?
B minus A.
What's that?
B minus A. Voltage B
Okay, yeah,
minus-
that would be, but what would it be relative to the current and that circuit element or resistor?
One. Ooh. One. Where's that one? It's a big number.
No, it's not a number.
Oh.
It's a symbol. What's your voltage change there? You don't see a delta V anywhere. And you're right, it would be V sub E minus V sub A, but we don't have that. We have a current moving this way across the resistor. What's your voltage change there?
IR.
RI, exactly. But what is your, that is the magnitude of it,
You mean like positive or negative?
positive or negative.
Oh, positive. No, because it's going forward.
It drops in the
I was
voltage.
gonna say no.
Yeah, remember what voltage is? Energy per charge. And the charges are losing energy when they go across the resistor. That's why, it doesn't get too hot, but that's why things heat up as they resist things. So this is a minus IR. The delta V here would be minus I times R. They didn't put a label R, but it is. Okay? And you're right, this delta V is VV minus VA. But if you're going in this direction, the voltage drop here is a drop because you're going across the resistor in the direction of the current. So it is a drop IR. Okay, minus IR. In B, the resistor is traversed. If you went this way, but the current is that way, that would be a plus IR because you're going from a low potential to a high potential, so you would be going up IR. The product is still IR. The delta V is IR. If you're going down, because this is the high side, the low side, that would be a minus IR. Low side, the high side would be a plus IR. Make sense? Okay. Now, in this one, C, if you're going from A to B here, what are you doing? Going up in voltage, because you're on the low side here, the high side here, minus here, plus here, so you're going up, plus E, that your delta V is plus E. I don't know why they use epsilon here rather than delta V, I guess just to make a difference. What if you were going that way? That would be a negative. You go across the battery from low side to high side, you're going up in voltage. If you're going from high side to low side, you're going down in voltage. Okay, and that's what those say. In C, if you're going this way, it's positive E, that way it's negative. Okay, good deal. So, the junction equations and Cherkaff's rules. I don't know why they did it. It just bugs me like crazy. There shouldn't be a space here. There should be FF apostrophe S, not with a space there. They did it in the last slide, they did it in this one. Use the junction rule as often as needed, so long as each time you write an equation, you include it in it a current that has not been used in a previous junction rule equation. I hit it. But that's
You
a
did
pretty
it.
strong fly.
It's not gonna die.
Hopefully I damaged it enough.
Oh,
Okay. Usually they're attracted to light, so I'm sort of surprised it took them this long to get here. Okay. In general, the number of times the junction rule is used can be used as one fewer than the number of junction points in the circuit. So if you only have 2 junction points in a circuit, you can only use 1 junction rule. If you have 3 junction points in a circuit, then you can use 2 junction rules. Otherwise, you just keep adding the same things. Okay, the loop equations. The loop rule can be used as often as needed, so long as a new circuit element, resistor, or battery, or a new current appears in each new equation. You need as many independent equations as you have unknowns. Now, you'll see, I think, and learn, the junction rules are really easy. So use those as many as you need. But then when you need more equations, use as many loop rules. Don't use extra loop rules if they don't get you anything extra. They're usually a little more complicated. Okay? So here's the problem-solving strategy using Kirchhoff's rules. Draw the circuit diagram and assign labels and symbols to all known and unknown quantities. There he is again. I'm missing that guy. Okay. Assign directions to the currents. Whether they're right or not, that doesn't matter, but assign them. Apply the junction rule to any junction in the circuit. Okay? However, make sure you got something new in every rule. Apply the loop rule to as many loops as needed to solve for the number of unknowns. Solve the equations simultaneously for the unknown quantities. You remember how to do that from math? And check your answers. Make sure you haven't made a dumb mistake. Whoa. They're not even going to show you an example of Kirchhoff's rules? Okay, I can't believe they're doing that. Going right past it and not showing a single one. There's example 18.4 and 18.5. Okay? Okay.
He's fast. He was just right in front of me. Are you sure? Oh, the little. It's 2?
And by the way, 18.5 has 2 different circuits in it. So, do you want to see at least one of those to see how they work? Okay. Okay. Tell you what I'm going to do. Let's dream on. Okay. Slap yourself. You're asleep. You must be dreaming. Okay. Let's see. Let's pause this for now. We're going to come back to it. And I'm going to open another PowerPoint that's just blank. Unfortunately, oh, look at that. It came really quickly. Okay. And we'll do current slide. Okay. Got some clean paper here. You want to do 18.4, 18.5, A or B? Just pick one of them. I don't care which. 18.5A?
Yeah.
Okay. Here's 18.5A. We start, okay. We'll start with a battery in this direction. That's a 14.0 volt battery. Okay. Plus side, minus side. Okay. Comes over here to a point they label as E. I messed up already. Okay. Come down from E, hit a resistor, and that's a 4.0 ohm resistor. You hit point B. Okay. From point B, you move this way, and you hit another battery, minus plus, and this is a 10.0 volt battery there. And from this, you hit a resistor, which is a 6.0 ohm resistor. And that takes you to point C. Okay? B goes down here to A with nothing in between. From A across here, you hit another resistor, and this is a 2.0 ohm resistor. Okay? Gets you across to point D. And by the way, this one up here was F. Okay? And from C to D, you have nothing in between. Okay, that is your circuit. Okay? Now, it says, I'm not going to do this. Yes, I guess I have to. They named the circuits, the currents for you. And I regret, because I wish they let you name them yourself. But they did name them, and they named this one I1 and gave it a direction. They named this one I2 and gave it a direction, which is totally wrong. I can tell that just looking at it. And they named this one I3 and gave it a direction. Okay? Now, which did I say you ought to do first? The junction law or the root rule or the loop rule? Second? No, you do the junction first. It's easier. Because junctions is just dealing with currents, and that's what we're looking for, the currents. We know the resistors. We know the voltage differences. We don't know the currents. That's what we're looking for. Now, the other thing about the junction rule is you use it one fewer times than the number of junctions. Name the junctions you see here. Is E a junction?
Yes.
Not really. That's just a wire. You don't have to even have a bend in it.
So
That's
would
just
B and C be junctions?
B and C are the only two junctions on there. And guess what? Since you have only two junctions, then you only can use junction rule once. It's usually one less than the number of junctions you have. So I would use C because there you see all three currents right there at C. And what do you see happening at C? Say again? I can't hear you.
If something is moving towards C.
Okay, what are moving towards C? You're interested in the currents. Okay, which currents are moving towards C? I1 is moving towards C. Second? A little again?
I2.
And I2, so I2 is also moving towards C. And?
The 6, I3 is moving away from C.
Away from, so you make that minus I3, and that's equal to 0. Okay? There you've got one equation, three unknowns. That's a simple one, but it's a very nice one to use. If you tried to do B here, you would see that minus I2 minus I1 plus I3 was equal to 0, but that's the same thing you got there. You just changed signs and you got it. So you can only use generally one junction rule less than you have total number of junctions, and here you only have two junctions. Okay, so you got three unknowns, I1, I2, and I3. How many loop rules are you going to need? 2, because you got one equation there, you need 2 more. Now you got 3 possibilities here for loops. Okay, any one of them will work. Okay, now I would choose that as a possible loop, right? Or this is a possible loop, right? Or as a loop. Any loop you want, but you only need two, so you pick which two you want. I'll say upper, lower, or around. Upper and lower. I like those two, so let's use them. Okay? And then you choose the direction you want to go around it. And I like going around this way, I think. Don't you? And then what would you say on the lower one? How about this way? Okay? We'll go around that way. Okay? So we'll start at a point. I don't care which one. You pick a point.
Anything on there I can pick?
A point, yeah. The A, B, C, D, E, or F.
B.
B? Okay, let's start at B. And you're doing the upper one?
Yes.
Okay, if you had said E or F, I'd have known you were on the upper one, but B could be upper or lower. Okay, you start at B and go in that direction. So the first thing you hit, going from B this way, is what? I think that's a 10, isn't it? Yeah, that one up there is. Okay, if you start at F, it's 14. She started at B, it's plus 10. So we got 10.0, that's voltage right there, plus 10. Okay, then what do you hit next? A resistor, and that's a 6 ohm resistor. And how much current's going through it?
3.
No, we don't know.
Oh,
I1. Okay, so current times resistance equal voltage, right? This is a voltage drop problem. Increase of voltage there, you decrease voltage going down a thing. Because this is the high side going to the low side. So it's a decrease. Minus I1R. Well, R is 6. So I'm going to put 6.0 I1. Sorry. Let me clean it up so it looks a little better. Minus 6.0 times I1. I didn't mean to erase that. Minus 6.0 I1. Resistance times current equal drop in voltage. Okay, continue around the loop. You hit nothing here, nothing here. What do you hit here? Plus 14. You're going up in voltage. So plus 14.0. And then you hit this, and what is that? 4.0 ohms, and what's your current there? Yes, we do.
Oh.
It's in this leg here. That's I2, right?
Oh, okay.
Okay, but I2, to show it better, is going in this direction, right? We're going opposite I2. You see? I2 was pointed down here, which means it must be pointing to the right there, must be pointing up here. That's I2. Not I1, but I2. This part here is all I2. This is the only part that's I1. Okay? So, you're going, if the current is going that way, that would indicate this is the downside, that's the upside, right? Because the current flows from high to low, right? So if that's the low side, that's the upside, you're going up I2 times 4 I2, right? Plus 4.0 I2. And now you're back at B, so the total voltage drop around the loop is 0. Okay? The total current going and leaving the junction is 0. Okay? Now, you want to do I3 next. I mean, the loop down here next. And you chose it this way, so I like it that way. Where do you want to start on this one? A. Okay, we'll start at A. We're going in that direction, sort of clockwise. So A to B, you hit nothing. Then you get here, and what do you hit? Which sign? Really? Positive. So you have a plus 10.0 here too. And then, same thing as before. Resistor, 6 ohm resistor. That's current I1. minus 6.0 I1. So far it's starting off identical to what that was because you're going right along the same way. But then past this, you hit nothing, nothing until you hit down here. And where are you here? I1 is going in, remind you, in that, I3 is going in that direction, right? So you're going down in voltage, right? Okay, because from the high side to the low side. So you're going down in voltage, how much? 2I3 minus 2.0 I3. And then you're back at A, so that's equal to 0. Okay. Now, Kirchhoff's rule, that's the best way to write it. But to solve a system of equation, I like to get it in first variable, second variable, third variable, equal constants, right? The first equation is perfect that way. So let's keep that just like it is. I1 plus I2 minus I3 is equal to 0. Just like we want it. First variable, second variable, third variable, equal constants. Okay? The next equation is not quite so nice. Okay? And I really, well, let's just leave it the way it is. It starts off with, okay, I'm going to get the I1 first. Minus 6, I'm going to leave off the point zeros. I1, right? Then go over here, plus 4, I2, right? Now you got to move this to the other side because that's a constant, and that to the other side. So that makes a minus 10 and a minus 14. That would be is equal to minus 24. You see how that works? Okay. Now the third equation. Again, it starts with a minus 6 I1 minus 2 I3, and bookkeeping helps to be nice too. And then move your 10 to the other side, minus 10. Right? I see no reason to carry the point zeros here. Okay. Now at this point, I look at that third equation, they're all minuses. I don't like minuses that much, do you? They're so negative. Okay, I'm just kidding, kind of. Okay, so why don't I make this plus, plus, plus? Change the sign of everything. We could do that to the line above, but let's not say we did. Now, 3 equations, 3 unknowns. Not a particularly easy thing to do. Have y'all ever done matrices? No. Too bad. Matrices make it much easier. Can I show you how to do a matrix? It's pretty straightforward. So hopefully it won't be too new. Now, I hope I got everything right when I was copying. Y'all were watching me, right?
Yes.
I didn't leave enough room, so I'm going to erase this because everything, all the information is below. Okay. And I'm going to write this as a matrix. Just that bottom thing as a matrix. Basically, all I do, I remember my I1s are my first column, my I2s are my second column, my I3s are my third column, and the constants are on the other side. Okay? So, all I'm going to write are my coefficients. 1, 1, minus 1, 0, and the constants. Okay? The next one is going to be a minus 6, 4, 0, minus 24. Right? The third one is going to be plus 6, 0, 2, and 10. Okay? Now, I noticed it down below, and I should have changed it then, but I'm going to change it now. Notice everything in the third row, second row is divisible by 2, right? So if you divided everything by 2, that would make it a minus minus 3, 2, minus 12, right? Minus 2, 3, minus 12. That just makes smaller numbers, it makes the whole thing easier. You can do the same thing to the bottom one, okay? That'll be a 3, 1, 5, right? 3, 1, 5. I would do this, write it out, but I just don't have much room. 3, 1, and 5. I've just divided everything, these coefficients here, every one of them by 2. That's legal. That gave me minus 2. Wait. I did that wrong. Minus 3. You let me get away with that.
I thought you said 3 for row 2. You said
Yeah, I did. Y'all,
you wrote it backwards.
yeah, sorry. Y'all are supposed to catch me on things like this. Dividing by 2. Glad. Oh, I didn't need to erase that last one, did I? Okay. Divide this by 2 is minus 3. That by 2 is positive 2. And that by 2 is minus 12. That by 2 is 3, 0, 1, and 10. Yeah. Okay. Now, you got your matrix there. I'll tell you what you want in your matrix. You want the upper left character number to be a 1. Guess what? We got it. Okay? We're happy there. Huh?
I've done this.
Huh?
I've done this.
You have it. Okay?
Wow.
Yeah.
Yeah. What do you want this to become?
0.
A 0. How do you make it become a 0? Say again? Okay.
No,
What-
you may be right.
What you do, use it, huh?
No, go ahead.
She said you do the inverse.
Okay. What you do is use that leading 1. That's what we call those, leading 1. And multiply that by 3 and add it to this one, and that'll make that a 0. Okay, there's 3 rules that you can follow in reducing a matrix. One we just done, multiply everything on both, everything in the row by a common number, or divide by, and we just did that. But don't multiply or divide by 0. Okay, that wipes it out. Okay, the next thing is, oh my goodness, you can multiply a row by a constant and add it to another row. That's legal. And the other thing, you can exchange any 2 rows you want to. Those are the 3 operations you can do. So what we want to do is do 3 times row 1 and add it to row 2, and that's going to make a new row 2. Okay? So since we're using row 1, I'm going to close it in like this so you'll know what I'm talking about. Since we're using row 1, we're going to keep it just like it is. 1, 1, minus 1, 0. Okay? Let's do what we just said. 3 times 1 is 3, minus 3 is 0. Ooh, just what we want. 3 times 1 is, plus 2 is 5. 3 times negative 1 is, plus 0 is negative 3. And 3 times 0 is, plus negative 12 is negative 12. Okay. Now, we want this third one to be a 0 too, don't we? Okay. Now I'm going to cheat a little bit. I can just look and see if I add those 2 rows together, that's going to give me a 0 down here. Right? So, row 2 plus row 3 is going to be the new row 3. Add those 2 together, you get 0, 2, 1, negative 7. Okay. All right. A big boo hiss here. Okay? Because the next thing I want, after you get a 1, first entry to be a 1, 0 is below it. You want the first non-zero entry in the second row to be a 1, and then you'll later mess with it. Well, I don't like having to divide by 5, though that's okay. I'd rather divide by 2, so I'm going to swap those 2 rows. Okay? So, since I've already used that top one, I'm going to erase it just because I don't have the room anymore. Hopefully I got everything right. So, let's do this. And this is a little tedious, I know it is. Especially, I'm probably boring you to death with it too. Okay. So I'm going to exchange these two rows and at the same time divide this one by 2. That's our new row 2 divided by 2. So I'm leaving row 1 alone, 1, 1, minus 1, 0. The new row 2 is going to be 0, 1, 1/2, minus 7/2. And the new row 3 is going to be 0, 5, minus 3, minus 12. I just swapped those two rows, but at the same time I divided this one by 1. Divided by 2. Multiply by 1. Okay, so we got 1 there and there. Now, there's 2 directions you can go now. One of these is to make it, I don't know if you remember the term, row echelon form or reduced row echelon form. You remember? Okay. Row echelon form, you want this to have a 0 below it. Reduced row echelon form, you want a 0 above and below it. The advantage of just getting 0 below it, as soon as you do that, then you're going to have your answer, I3 is equal to something. But then you're going to have to plug back in here and then plug back in here, so you have to do what they call back substitution. If you take a few extra steps on this side and put zeros above and below your leading ones, then you can just read your results. So which way you want to do, just reduce it, row echelon or reduce row echelon. 0 is just below or 0 is above and below.
What's the above? What's the one way? The above.
That's reduce row echelon. You want to do it that way? Okay. So, first thing we want is to get a 0 up here and a 0 down here. Those are 2 different steps, but we can do it both at the same time. So, since we've gotten that one right, I hope I got it right. So then I'm going to erase this one. I normally wouldn't. I'll just write it all over the paper, but I just don't have much paper. Okay. Yuck. I didn't mean to erase that part. That was, no. This was I1. Okay. I probably could erase that, but let's go. Okay. So what we're going to do to get this to become a 0, same as we did before, minus row 2 plus row 1, right? Minus this plus that, which is going to make a 0, right? Okay, so that's our first step. So minus row 2, minus 0 is 0, plus 1 is 1. Fantastic. Minus 1 plus 1 is 0. Minus 1/2 minus 1 is minus 3/2, right? And minus 7/2 is 7/2 plus 0 is 7/2. Okay? I don't like fractions, but we're stuck with them. Okay? We're using the second row, so just leave it alone. 0, 1, 1/2, minus 7/2. Okay? Now, we want that 5 to become a 0, right? So what are we going to do? Using this 1, minus 5, row 2, plus row 3. That'll do it, won't it? My writing stinks. So minus 5. That's still pretty bad. So minus 5 times 0 is 0, plus 0 is 0. That's good. We didn't want that to change. Minus 5 times 1 is minus 5 plus 5. That's a 0. And minus 5 times 1/2 is minus 5/2. Minus 3, which is minus 6/2, that would be minus 11/2. Right? And then minus 5 times minus 7/2, that would be positive 35/2, right? minus 24 halves. So positive 35 halves minus 24 halves, that's going to be positive 11 halves, right? That's working out nicer than I thought. Okay? So now we got a 1 here, 0 is below, a 1 there, 0 above and below. We want this to become a 1. How do we get that to become a 1? Not going to need this anymore. I hope I did everything right. This is really working out nicely. Believe it or not, even with those fractions in there, it's working out well. Okay? I want that negative 1 half to be, negative 11 has to be a 1. So what am I going to have to do to make it a 1? So again, you can multiply the same thing by anything. What multiplying by negative 2 11ths? Will that work?
Oh, yeah.
Okay. But, and you multiply that, it stays a 0, that stays a 0, that becomes a 1, and that becomes a negative 1. Yeah. That is really nice. So what we're doing is row 3 times negative 11 halves. No, 2 11ths, I'm sorry, 2 11ths, okay? So our new row 3 is 0, 0, 1, minus 1. Guess what we know now? I3 is equal to negative 1 amps. And what did I say before? Oh no, I didn't say that before. I said I2 was going in the wrong direction, but this tells me I3 is going in the wrong direction too, which I find surprising. No, not that surprising. Okay. So I3 is equal to negative 1. You got it right there. Okay, next thing we want is to copy the other two down. 1, 0, negative 3 halves, 7 halves. And this one would be 0, 1, 1 half, negative 7 halves. Hope I've done it right. Okay, so I don't need the second one anymore. So just, I wish I could combine some more steps, but there aren't that many you can combine. Okay. What do I want next? I got a 1 here, 0's below, a 1 here, 0 above and below, 1 here, I want 0's above that. So how can I make that negative 3 halves become a 0? Using the third row, the one with the leading 1 in it. Multiply 3 halves times row 3 and add it to row 1. Right? That's a legal move. And that will make, when you're using row 3, so it's 0, 0, 1, negative 1. Okay? 3 halves times 0 is 0, plus 1 is 1. That didn't change. 3 halves times 0 is 0, plus 0 is 0. That didn't change. 3 halves times 1 is 3 halves, minus 3 halves, that makes that a 0. And 3 halves times minus 1 is minus 3 halves, plus 7 halves is 4 halves, right? Which is 2. So guess what? I1 is equal to 2 amps. Okay? And then we'll do the same thing to the middle one, or something similar to it. We want that 1 half to become a 0. How do we get that? Multiply the 1 by negative 1 half and add it to it. So negative 1 half, row 3, plus row 2 is going to be the new row 2. So negative 1 half times 0 is 0, plus 0 is 0. Good. Negative 1 half times 0 is 0, plus 1 is 1. That's good. Negative 1 half times 1 is negative 1 half, plus 1 half is 0. Negative 1 half times negative 1 is positive 1 half, minus 7 halves is minus 6 has, which is minus 3. So this tells us I2 is equal to negative 3, right, amps. Which I told you, I know that one's wrong. Because you see, this voltage is going that way, that one's going that way. I knew that one was backwards, okay? So, I1 is 2 amps, I2 is negative 3 amps, which means it's going in the other direction. So just change the sign here and drop that. And I3 was negative 1 amp, so just change the sign on that and make it a plus 1 amp. And there you got your circuit, okay? And sure enough, if you look at this now, 2, okay. Looking at it the way we really drew it now at the end, coming in is I1 and I3. That would be 2 and 1, and they make 3. Absolutely. And then you can go around and check your others too. But that's what you got. So, all right, that's Kirchhoff's rule. And there are other examples there. You certainly can do it. There is a tip here. More current goes into the path of less resistance. You may have heard the statement, current takes the path of least resistance. For a parallel combination of resistors, this statement is inaccurate because the current actually follows all paths, blah, blah. The most current, however, travels in the path of least resistance. So that means next time we will start with RC circuits. And since it is so late and y'all have been so good to stay, I'll let you go 4 minutes early. So I'm cheating you out of 4 minutes. Actually, it's 3.5 minutes out of your tuition dollars. I feel like I'm really ripping you off. Okay. All right. Take care. We'll see you on Wednesday. I need to find my marker here. Where's my marker? There it is.